Hey everyone, welcome to another episode of Black Guy Does Physics, where around these parts we record a whole episode without having your mic turned on. Anyway, if you have any issues, questions, comments, suggestions, hey, there's a box down there somewhere where you could do all this stuff. And while you're doing that, you could definitely hit that subscribe button. Subscribe, man, so when I drop new stuff, hey, you get it. With that being said, let's get it cracking. Ah. When am I going to learn not to stop hitting this table? It's tough. It's hard. Okay. All right. Today we're looking at Mechanics 2009 number 2, which from my introduction you could tell that I did yesterday or another day, and the mic wasn't on. I'm hella pissed. But let's get it cracking. My boy Spicy asked me to do this one also. So let's go into it. Once again, you see a diagram. From the diagram, you try and figure out what's popping. So the thing that's popping right here is that you see this thing. This thing is like, this thing could actually like rotate, right? And whenever you see something has an axis and there's some rotation going on, in order for something to rotate, there must be some torque. So torque is the concept that comes into my head. So you have to know all the trappings that come with torque. But torque, I'm going to explain more than I usually do because I don't think Spicy has this information already. So I'm going to let it write down some more stuff. So the video might take a little bit longer. But once again, you could also just fast forward that junk if you don't need to know that junk. Just, 1.5. It works. All right. So torque. For torque, you could have, it is that the two equations that usually pop in mind is torque net is equals to I alpha, and the torque is equals to the R cross F. That's a fancy way of saying it. You could also say it's R perpendicular times F, or you could also say it's R F perpendicular. I use it like using this one here, R F perpendicular, because it just makes life easier, where F is the perpendicular part of the force to the object, and R is the distance of the object from the axis of rotation. And with torque usually comes forces. So everybody and their mama should know about forces. For forces, it's usually just F net is equals to MA. So if you have to do something, that's the relation. And there's a relationship between the force and the torque. It's in the acceleration. The acceleration is going to be equal to R alpha. I don't know if you're going to use all these things in this. Chances are not, because usually when you use this, you're talking about like pulleys and crap like that. Pulleys where the actual pulley has a mass. But in this case, nah. We just have a rod that looks like it could rotate. Once again, if you have a rod that's hanging like this and it could rotate, then SHM, I think that is, not SMH. SHM, yes, which would be simple harmonic motion. And for simple harmonic motion, there's a bunch of things that's true, and I'll explain them as we're going along. But it's simple harmonic motion. For simple harmonic motion, if you see a spring, you could use simple harmonic motion. For springs, this is a side note. Springs, it's either energy, simple harmonic motion, or spring forces. So that's a side note. But simple harmonic motion, whenever you see something could oscillate back and forth, think simple harmonic motion also. So torque and simple harmonic motion. Now that we have that out of the way, we go read. Given a long, thin rectangular bar of molten mass M, length L, pivot. Ooh, pivot, told you. Attached at one end. It's non-uniform mass density. So if it's non-uniform, what that means is that, the center of mass isn't in the center. When something is uniform, the center of mass is in the center. What's the center of mass, you might ask? That's a joint where all the weight acts. So for regular uniform objects, it's in the center. So, cool. That means we don't know where the center of mass is. The center of mass is located in... Oh, sorry, sir. The center of mass is located at X. So they're telling you where the center of mass is. Dope. Cool, I'll take that. From the end with the pivot, you are to determine the rotational inertia IB. So sweet. I will have to use something over here of the bar about the pivot by suspending the bar from a pivot as shown above, allowing it to swing. So swing, that means I should be doing something like this. Express all algebraic answers in terms of IB, blah, 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 blah. Okay. By applying the appropriate equations of motion, the frick do they mean by equations of motion? Write down the differential equation for the angle theta that the bars make with the vertical. So that means that this thing, if we have a bar here, hopefully I could draw a bar. Is this a, nah. ah, a bar here, right? They're asking you what is happening with theta. Let me put a vertical line here. So they want to know about theta here. So that's your theta. Awesome. So, cool. Equations of motion. What does this mean? Well, most kids, they will think that the equation of motion would be like, yo, v is equals x over t, v squared is equals those equations of motion. But when you're talking about those equations of motion, you're talking about constant acceleration, constant velocities type of thing, right? But here, if you're talking about something swinging, right, and then didn't give, and you're talking about the moment of inertia, then there's no way that you're going to use those things. You have to use Newton's version of Newton's second law, or any version or iteration of Newton's second law. Newton's second law, as you should know, is F is equal to ma. The acceleration in that thing is what makes it, you're talking about motion. And if you didn't know, Newton's three laws of motion are all about forces, because without forces, I shouldn't say that, but forces generate acceleration and motion in general. Okay, so here all they're saying to you is that you're going to write what is true. And what is true when something is rotating in terms of forces or whatnot is that the torque net, it should be equals to I alpha. Cool. So this is the junk that is true. So since it's true, you just write what it is. So the question now is, if this is true and I have to write it, I have to write what torque net is. So if I want to figure out what torque net is, I have to figure out all the forces that are acting on this thing. So if the axis of rotation is up here, the only thing that's acting on this thing is the weight, which would be at some distance x. So I'm going to call this, what am I call this? mg. And this distance is x. Any forces that is acting up here will be null and void when you're talking about the torque. Why? Because it will be acting at the axis of rotation. Okay, I wish my line was straighter, but whatever. So my torque would be produced by this force, the weight, since it's the only thing that's acting. Therefore, as I stated before, I like using this stuff, RF perpendicular. So I want the perpendicular part of this force. See right there. And if this angle is theta here, then that means that this angle is theta there. If I have to explain that to you, you shouldn't be doing no AP mechanics, man. Get out of here. So that side is going to be mg sine theta. Good. That's what it's supposed to be. So the torque that is produced by that should be the force, or the radius, which is x, times the perpendicular part of the force, which is mg sine theta. And that should be equals to I. In this case, I is IB. And then because they're asking you for the differential equation, you should know that in terms of calculus, that the acceleration is the second derivative of the displacement. So since this is the angular acceleration, then what we're going to have is that the angular acceleration is the second derivative of the angular displacement. It is what it is, because you know dx dt is equals to v, and dv dt is equal to a. That's what we just did. So if you move that over, if you want, I think you could leave it like this, but if you move this over, there's a reason why you want to actually kind of move this over, why not? You'll see that it becomes this stuff. Okay, and you're done. That part is done. Easy. Thank you, AP. We love you. Okay, so now it says by applying a small angle approximation. What the hell is the small angle approximation? If your teacher didn't tell you this, you should know. Sine theta is approximately equals to theta if you're talking about really small angles between like 0 and like 10 degrees or 5 degrees or something like that. And I also think tan theta is approximately equals to theta. I don't know about a tan one, but I think it's true also. You could test it. Just either Google it or punch it in your calculators, broskies, and then you'll figure it out. But that's what the small angle approximation is. Calculate the period. So crap, I need to know the period of the bar's motion. So no, I'm in this test. I don't know what to do, man. Well, I can look at my cheat sheet. The only places I see period is that the period is equals to 1 over f, or I see that the period is equals to, no, let me do it the way I remember, because I haven't looked at these equations. It would be that omega is equals to 2 pi f, which is equals to 2 pi 1 over t, or 2 pi over t. And you could rearrange to that. So I'm looking for the period. Now, once you see the word period and you're like, you're stuck, the only place that you could go is simple harmonic motion. If you don't have the exact values for these things, the only place that you could go is simple harmonic motion. Because you know that if you have simple harmonic motion, you could calculate the period of something. So now the thing is, okay, what do I do? They gave you this. They said use a small angle approximation to your differential equation. That means that whatever you're doing, you need to do this junk. So let's write it back down. So we're going to have d squared theta over dt squared should be equals to, what is this? IB minus IB plus mg. Oh, no. The force, one of these forces, I'm mixing up. Oh, my math is horrible. Why no one told me? Sine theta over IB. Sorry. I ain't starting over that whole video for that mistake. Hell no. Y'all boys be all right. X mg sine theta over IB. But you can see there's a negative here because of the force. Force is causing the object to, it's a restoring force per se, so there's a negative there. Anyway, this is what you have. So if you use the small angle approximation, that sine theta becomes this stuff, becomes just theta. So what you will end up with is minus x mg theta over IB. And I'm going to rewrite this. No, I'm good. Over IB equals to d squared theta over dt squared. So the question is now, how does this junk help you? Well, in order for this to be very clear and very quick, you'd have to pre-know some information. And what I'll do now is like explain some things to you. So, in order for something to be a harmonic oscillator, we have to go back to this thing which is called the spring formula thingy, which is F is equals to minus kx. Right? That's the spring force equation. F is ma, and this is minus kx. The reason why this is a harmonic oscillator, as your professor or your teacher should tell you, is that the force is always perpendicular to the displacement, not perpendicular, proportional to the displacement. It's a 1-to-1. It's directly proportional. And it's always trying to retard the motion. It's always trying to reduce or bring it back to equilibrium. That's why the negative is there. Now, if we took that mathematical steps, we could do this then. M is d squared x dt squared equals to minus kx. Dope. All right, cool. Then I could have d squared x over dt squared equals to minus kx over m. So, if you get anything in the format of where the displacement to the second power, the time derivative of the displacement to the second power, or the second derivative of the displacement is directly proportional to the displacement, then this is an harmonic oscillator. So you could see here that this and this. So in essence, broskies, it's only two things that you could have: angular displacement and linear displacement. So it's either x or theta for your class. Anything else you're not going to be dealing with right now. So it's either x or theta. So these are the only formats that you're going to see. It's either d squared x over dt squared is going to be directly proportional to x, or d squared theta over dt squared is going to be directly proportional to theta. And there's some negative sign there. That's what's happening. All right, cool. So you only have those two things to do. Dope. So if you have it in this format, you're good. And you're like, oh, crap, it's a harmonic oscillator because it is in this format. Yay, great. But the question still asks you to derive what the period is. So now the question is, how the frick do I find a period? Well, this goes to more things where if you were in the exam and you came with information that was your professor or your teacher told you this already, then you'll be Gucci. Why? Because you would have remembered something and you'd have been like, oh, I could do this. Well, I'll explain this thing. As I said from the jump, this is going to be a little bit longer. So let's see where this crap comes from. This is a circle, right? And what we're going to do is that we're going to have this line running across the middle of the circle, and we're going to have the particle here. So I have a particle going around, but this particle is literally, the movement of this particle around the circle here is going to be projected onto this thing. So it's going to go back and forth like this, just like a harmonic oscillator. So you could see here, if I say this is my thing, and then this is my thing there, that's my center, that's my radial line, and then this is my projection down here. Sweet. So when this thing is like at some angle theta here, then this thing would be at some distance x here. I don't like that pink x. Get out of here, pink x. So that would be like that. So this would be r, where r is the radius there. So you could see, if I wanted to figure out what was this thing here, this x, then I could use, I think it's x would be equals to r cosine theta. X would be equals to r cosine theta. Oh my God. Yes, this is true. Now, what we'd see now is x is equals to, instead of putting r, I'm going to put a. Why am I putting a? Because r, the radius, is the same thing as the maximum amplitude of what this thing could move. That's the maximum that it could do. The minimum would be 0. The maximum would be r. So the amplitude is the maximum of the oscillation. That's your a, and that's r. I'm also going to say this is cosine omega t. Where did this come from? It comes from the fact that omega is equals to omega is equals to theta over t. Therefore, theta is equals to omega t. So the short version of this now is that if I want to figure out the velocity, I would have to take the differential of this stuff, because as we said before, dxt dt is dv is v. So when I differentiate cosine, I end up with a minus sign. So there's going to be a minus here. There's going to be an a here because I'm not touching the a because it's a constant, and then there's going to be a sign here. So the question is, what the hell do we do with this junk? Well, what we do is that we differentiate what's inside here. In essence, what differentiation is, if you don't remember, is that the power that's here, you're going to minus 1 from it, and then you're going to multiply by whatever is there, and you're going to take it out. So in this particular case, this is going to be an omega, and you're going to write down omega t again, because the differential of omega t is omega. Ta-da! So that's your v. Now, if you want to know what your Vmax is, which we're going to put, not that it's necessary here, but just for extra information, your Vmax is going to occur when the maximum value of sine theta. The maximum value of sine anything is 1, so your Vmax is minus a omega. Ta-da! So now, if I wanted to figure out the acceleration would be the differential of the velocity, dv dt. So I go again and I go, okay, when I differentiate sine, I end up with a cosine. So this junk is going to be the same out here, a omega, and then I have to put cosine, and then I have to differentiate inside here again. When I differentiate inside here again, the omega t, once again, same rules, minus 1 from there, that would give me 0, and then you multiply this, that would give me omega out. So I have to multiply by another omega. That means that becomes omega squared, omega t. Right? Now, with that being said, we go, what's the Amax? Once again, I don't think you need it here, but why not? It's the maximum value is when this stuff is 1. So that would be, that's your Amax. Nice and simple. Now, the trick here is that, yo, son, this junk, let's pink it up. Nah, let's red it up. This together is X. See? See? So I could rewrite A as minus x omega squared. Dope. So guess what? This junk is A. Oh my god! So instead of putting this here, I could put minus x omega squared is equals to minus k over mx. Oh my god, Becky. Look at her butt. It is like so big. So there you have it. So when there's an harmonic oscillator, then you have omega should be equal to the square root of k over m. In other words, omega is going to be equal to the square root of whatever this junk is. Whatever is in front of this thing. So if we apply it, if we apply it there, then we're going to see that omega should be equal to the square root of x mg over ib. See that? And then if you have omega, then you could solve for t, because t should be equals to, can I do some math? I think it's 2 pi over omega. And then you could substitute. That's it. That's how you solve that. Sweet. That's done. Let's see here. It says, describe the experimental procedure you would use to make this additional measurements needed to determine IB. You use your measurements to obtain IB and how you would minimize error experimentally. Okay, that's important right there. This part I would talk about. I'm not going to write down the whole thing here because in the AP solution things, you could always see how they explain the labs. But I will explain. Let me write this out properly. Let me copy this because I can't remember from the top of my brain. I will explain. No. Paste. So that means red. That means that t should be equals to 2 pi over, so it'd be square root IB, whatever, I just put it down there, xmg over IB. What this means is that if you want to figure out the period experimentally, then, and in any case, any one of these experimental problems that you have, AP is always going to set you up with an equation first. You're going to use the equation to your advantage. The equation is going to be there to tell you exactly what you need to measure. Because you, as I tell my students all the time, the equations and the things are interrelated. The concept and the whole whatever is interrelated together. So I'm saying, so the equation is the concept, and the concept is the equation. So when I look at this junk, I see I have t 2 pi x mg ib, right? I subscript b. So if I want to figure out the period, then obviously pi is a constant, g is a constant. I would have to measure the mass, so I'd have to get the mass of the rod. I would have to know what x is, so I'd have to measure x. How do you get x? X would be the distance, the center of mass of the thing. Well, for the center of mass of something, if you wanted to get the center of mass, then all you have to do is just balance it. Because it's a beam, you just balance it on something. If you balance it on something, that would be the center of mass. Like if you have a ruler or something, you just balance it wherever it is. That would be, balance it on your finger, or balance it on an edge or something. That would be the center of mass. And then from those information, you could try and get your, you need your IB too. But you could get the period. I'm sorry, you're calculating IB. You could get the period. You could measure the period, because the period is just how it swings back and forth. So what would you do? You just let this thing go. Would you swing this junk one time? Oh, one time, period. No, because you're in a lab, and in a lab you're gonna there's some error, you know? You can't magically just time this. So you just swing it back and forth. You personally don't swing it back and forth. You let it swing back and forth like for 20 oscillations, right? And then when you get the time from that using like a photogate or something, then you have divide that by 20, give you one period. Now, you're going to take that multiple times, at least 5 times. You're going to repeat that thing like 5 times. With that thing, then you're reducing your uncertainties, aka you're reducing your errors, because you're repeating the experiment multiple times. For every experiment, you definitely need to do this. Something which I never said, which is very important. Remember, in order to get this thing here, you use the small angle approximation. So if you use the small angle approximation approximates that you're starting this junk from a small angle, which means that you're going to be using like a 5 degree or a 10 degree angle from the vertical. You can't be putting this junk at like 45. Then it doesn't work, bro. It does not work. So you have to remember that. And with that, you're good. You're Gucci. You just set it up for any experimental problem that they give you on this AP things. Just look at the equation, and from the equation, just look at the things that you can measure. And from those things that you could measure, anything that you could measure multiple times, you measure multiple times. Anything you could do multiple times, you do multiple times. Why do you do these things? To reduce uncertainty and error. In some cases, you're going to have to plot a graph or whatnot, but this one doesn't deal with that. If I run into one that deals with that, then I'll deal with that, okay? And for part C, you can look that up. I think I already answered it in what I just discussed already. But definitely check out the actual solutions from AP, and you'll see what they're saying. And you could compare it to what I'm saying or whatnot. So with that, I think I'm done. But no, I'm not done. I forgot. Remember, kids, don't be a moo-moo.